Hi everybody, this is Dr. Bricker here with some hints for homework number 9, which is mostly over chapter 28, but does have a couple of questions over chapter 25. The first one here is one recent study has shown that X-rays with a wavelength of 0.005 nanometers can produce significant numbers of mutations in human cells. And we want to know, in part A, calculate the energy in electron volts of a photon with this wavelength. Okay, so we're given the wavelength. We want to know how much energy that corresponds to in electron volts. And part B, assuming that the bond energy blocking, holding together a water molecule is typical, so you have to look at this table 25.1 in the textbook. Estimate how many molecular bonds could be broken with this energy. Okay, so given this energy and using table 25.1, how many bonds could you actually break? All right, let's take a look at this. Okay, so the end of chapter 25 is where we start to transition into thinking about light as being an actual sort of like massless particle. So the energy associated with a photon, this little quanta of light, is h times f. And h is a new constant that we haven't seen before. Planck's constant. It's over here, 6.63 to the minus 34 joules times seconds. So h times f will give you the energy of a photon, and f is the frequency. We know that the speed of light is the frequency times the wavelength. So if you want, you could solve for frequency in this formula, plug it in here, and have this for the energy of a photon in terms of the wavelength. Now it looks more complicated than it is. H is a constant, C is a constant, this is the wavelength. So if you know the wavelength, you could easily figure out the energy. If you know the frequency, you could easily figure out the energy of a photon. As a reminder, the speed of light, 3 times 10 to the 8th meters per second. Now if you work with this stuff a lot, there's an easier way to kind of to solve this if you know the wavelength of light in nanometers. So h times c, right, that's a constant, that's a constant. So instead of doing this times this every single time, if you want to do just h times c already for you, this is 1240 electron volt nanometers. So you could take this and plug it in here for hc. It's already multiplied out. So if the wavelength is given in nanometers, it's a pretty easy calculation. Okay, remember that 1.6 to the minus 19th joules is 1 electron volt also. Okay, just a different unit of energy. So if we do have the energy, or sorry, we have the wavelength in nanometers, then the energy is hc divided by the wavelength, and then we could use our new fancy h times c already being 1240 eV nanometers divided by the wavelength, 0.005 nanometers. Then you can see how easy this is. The nanometers cancel out, and then you're left with the energy in electron volts. Okay, good. So it's useful if the wavelength is given in nanometers and you want the energy in electron volts. I mean, this comes out in electron volts. You could then convert it to joules if you wanted to. So in part B, look at table 25.1. You know how much energy you have now. That table will give you the energy to break a molecular bond, and then you can figure out how many bonds you can possibly break with this energy photon. All right, let's look at the next one. Okay, so we have the intensity of electromagnetic radiation from the sun reaching the Earth's upper atmosphere. So this is the amount of power per square meter. Assuming that the average wavelength is 680 nanometers for this radiation, find the number of photons per second that strike this area. Good, so this is the power per area. This is the area that we're talking about, so we could figure out the amount of power. And if we know the wavelength of each of these, right, here's the wavelength, 680 nanometers. If you know the wavelength, you can calculate the energy. So we know the energy that each of these photons has. Okay, let's put it all together. And remember, if you hit review here, this will go to the exact correct section in the book. Okay, let's take a look at this. Okay, so given this intensity, 1.37 times 10 to the third, and remember what a watt is. It's a joule per second. And then I still have square meters, so watts, joules per second, square meters. So if you multiply it by the area, this 1.3 square meters, this will tell you how much energy per second you have. So let me actually do that. Okay, so 1.37 times 10 to the third times 1.3, 1781. And this is joules per second. Now we want to know how many photons that corresponds to. They're asking for how many photons per second. This is how many joules we have. 1781 joules every second. And we know one photon. We want to know how much energy one photon has, right? So if I knew the energy for one photon in joules, this would tell me how many photons per second. So given the wavelength here, I can calculate the energy that one photon has. So let me actually do that. Now I need this energy to be in joules, so there's a couple ways I could do this. I could just use H times C divided by the wavelength. Let me do it that way since I did it the other way last time. I want this to come out in joules. I could use the 1240 eV nanometers, get the answer in electron volts, and then convert it over to joules. Or let me do it this way. I'll just expressly put in H, which is 6.63 to the minus 34th joules times seconds, and then speed of light 3 times 10 to the 8th meters per second, and then divided by the wavelength, which is 680 to the minus 9th meters. And if you look at this, this will come out in just in joules. This meter cancels with that meter, that second cancels with that second. So this will be the energy in joules for just one photon. This is what goes here, right? That's the energy for one photon. So if you know you have a total of 1780 joules per second, and each photon has a certain amount of energy, then you could calculate the amount of photons per second. Okay, don't be surprised if it's a really big number too. All right, excellent. Let's look at the next one. Okay, so just a couple of questions. The first two are from chapter 25, just getting us into this idea of looking at light as sort of a massless particle. And then chapter 28, several different concepts come up. This is sort of the beginning of modern physics. So any physics since about 1905 is called modern physics. This is something called the photoelectric effect, this problem. So when you read through chapter 28, that's one of the first things that you'll see. And this is what Einstein actually won the Nobel Prize for. So it's really pretty cool stuff. So electrons are emitted when a metal is illuminated by light of wavelength less than 383 nanometers. So remember, the smaller the wavelength, the higher the amount of energy we have. Okay, but for no greater wavelength. So this wavelength, 383 and less. That means more energy. So the idea with the photoelectric effect is you shine light on metal. If the light that's hitting the metal has enough energy, the electrons can grab a hold of that energy and be liberated from the metal. But they can only, one photon comes in, they could grab hold of all of the energy of the photon and use it. But if the energy is not high enough, then the electron's not liberated, and it can't keep storing it up like a small amount of energy, small amount of energy, small amount of energy, and then be released. That's not how it works. There has to be enough energy contained in one of the photons coming in. Okay, and then when it says what is the metal's work function, the work function designates the lowest amount of energy that the photon has to have. So the work function, again, that's the lowest amount of energy to actually liberate the electron, and it's measured in electron volts here. Okay, let's take a look at this. Okay, so here's the wavelength of the incoming photon, and we're trying to liberate the electron. So the maximum kinetic energy that the electron could have after being liberated, so kinetic energy after liberated, freed, however you want to think about it. This is the energy of the photon that's coming in, or sorry, this is the energy, so the photon that's coming in, the electrical energy of the photon. So hc over the wavelength, that this is for the photon, and then this is the work function. That's the minimum amount of energy to just release it. Work function. So energy of photon. Now if you just get to the position where you're going to liberate it and it doesn't have any additional energy, so to just liberate it, this kinetic energy is 0. Just liberated. That's what we have going on here. We've just freed it. We're just trying to figure out the work function. So the work function then in this problem turns out to be the energy of the photon, right? If this is 0, we arrive at this equation. So hc over the wavelength. And then I could use my 1240 eV nanometers like I did before, divided by the wavelength. Remember, h times c is 1240 eV nanometers, and then divide by the wavelength, 383 nanometers, and then that will get you the work function. So you could actually figure out what kind of metal it is. If you calculate the work function here, you could look in a table and see what sort of metal this corresponds to. Okay, let's look at the next one. Get some more practice with the photoelectric effect. Okay, so electrons in the photoelectric experiment emerge from a copper surface with a maximum kinetic energy of 1.1. Okay, so in this problem, they're not just being liberated, they are being freed and they have a little bit left over, 1.1 eV. And then we want to know what is the wavelength of the light. So you'll have to look up the work function of copper. So, take a look at the section of the book, you can get the work function of copper. And we want to see what wavelength of light we have. So let me set this one up. Okay, so here's what we just found in this, or what we just saw. This is given in the problem. So I'm going to put check mark here. This you have to look up for copper, so I'll put check mark here. H is a constant, C is a constant. The only thing that you don't know is the wavelength. Just be careful with the units when you do this. You'll have to do some algebra. So essentially we have to add the work function to both sides. And that's hc divided by the wavelength. And then a little bit of algebra involved, but not too bad. I'll just put dot, 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 solve for the wavelength. Again, just be careful with the units. Now, this is in electron volts, this is in electron volts. So if you use H times C in electron volt nanometers, you should have no problem. Okay, so just be careful, put the units in, and then solve for the wavelength. Okay, so again, this problem, the incoming photon has more than enough energy. We overcome the work function, and then we have some left over. That's what's given in the problem, the kinetic energy. Okay, so not quite done here. A couple more steps. Solve for the wavelength. Okay, let's look at the next problem. Okay, so a photoelectric experiment finds a stopping potential of 1.93 volts when light of 200 nanometers is used to illuminate the surface. Okay, so essentially you shine light in, you free some electrons, you would measure some current because now you've got free electrons. They could drift from one side to the other, moving charge. That's what current actually is. So stopping potential is you want to stop this from happening, and the reason you do that is then you can deduce what the work function is. So let me hit this review button here. There's a nice picture, and we can take a look at this. Okay, so this again goes to the textbook, the correct section. Okay, good. So you shine light in here. This is a piece of metal. Electrons are freed, Now you've got a negative charge here, and they would drift across to the other side, and that's what current actually is. Okay, so now if you set up a voltage here, and you've got some free charge, it's easier to get them to go across. But what if you want to stop this from happening? You shine light in, electrons are going to come across the other way. So this is a negative plate because it's hooked up to the negative part of the battery. Positive, hooked up to the positive. So in this arrangement, electrons want to go across here. Now if we stop the current from going, we could work backwards and figure out what the work function would be. Or if we know the work function, we could figure out the intensity of the light. So this light has to have a high enough frequency, or another way of looking at it, low enough wavelength to actually free electrons, and then you can get current. And this actually works if you have any kind of smoke detector at your house, or lights that come on at dusk. This is the idea behind it. So let's reverse the voltage there. Let's see if we have it here. Trying to see a better picture. We might just have to go with the picture that we had up there. Yeah, okay. So I'll have to use that picture. I was hoping there was one with the battery already reversed, but it doesn't look like it. Actually, okay. So it's not as good as the picture above, but this is the idea. You would have electrons freed, and then they would go across this way. Now, if you reverse the battery like this, now the electrons don't want to go across. So you could adjust the voltage of the battery, and you stop any of this from happening. Essentially, you're taking the kinetic energy that the electrons would have had when they were liberated and turning it into electrical potential energy. So the maximum kinetic energy turns into electrical potential energy. Okay, so let's use that idea. Keep this in mind. I'm going to go back up to this picture again. Okay, sorry, this is at the very beginning. So this battery, you flipped around and you stop current from happening. You're taking the kinetic energy that the electrons would have had and turning it into electrical potential energy. Okay, so let's put this all together on paper. Okay, so we saw this before in the previous couple of problems, but in this problem, we are taking the kinetic energy and turning it into electrical potential energy. So from chapter 24, electrical potential energy was Q times V. It's just here I already know the Q, that's an electron, and the voltage to stop is just called V stop in this problem. And it's actually given as 1.93. So we can take this and plug it in for the maximum kinetic energy in this formula. They're asking for, what is the metal? Well, if we could figure out the work function, then we could deduce what metal it actually is. Okay, so E times V stop is hc over the wavelength minus the work function. A little bit of algebra. Work function, putting it over here, is equal to hc times the wavelength minus E times V stop. So here's how I would do this part. H times C, this is 1240 eV nanometers, divided by 200 nanometers. That's the energy that the photon has. And then minus E times V stop. So if you want to figure out energy in electron volts, and you have the V in volts, it turns out, and go back to chapter 24 for this again, V stop is given. This, if you want to do in SI units, this would be 1.6 to the minus 19th. But if you want to get the energy of E times V in electron volts, it just is 1.93 eV. That's the use of it. It seems probably too easy, but if you measure the voltage in volts and you're talking about an electron, the energy that that electron has is 1.93 electron volts. Now you could do this as 1.6 to the minus 19th coulombs times the volts. This would come out in joules, and then when you convert it back to electron volts, you'd get the same thing. Let me actually show you that. 1.6 to the minus 19th coulombs times V stop, which is 1.93 volts. And then remember, a volt is a joule per coulomb, so this would come out in joules. Let me actually do it. Well, I don't want to do it. It comes out in joules. I'll do it. All right, that might be a little bit better. I'm trying to see which way would be the better to show you sort of the magic of this. Times 1.93, 3.088 times 10 to the minus 19th joules. Oh, but now we want to turn that into electron volts. And I know it's 1.6 to the minus 19th joules for 1 electron volt, and then you get the same thing, 1.93. So here you're taking 1.93 and multiplying it by 1.6, you get this number, but then you're dividing it by 1.6 to the minus 19th again. So if you don't feel comfortable with realizing if V is in volts and you're dealing with an electron, that is the energy, you could just do it this way, and then you'll see you'll get the same thing. Okay, so whatever this turns out to be, this is the work function, and then you'll have to look up in that table what metal this corresponds to. And then the second part, part B, was talking about how does the stopping potential depend on the intensity. So make sure you read through that part of that section 25.2 to see how that all works out. So you'll have to do a little bit of reading for part B. All right, let's look at the next problem. Okay, so sodium has a work function of 2.8. What is the longest wavelength of light that will release an electron from the sodium surface? Okay, so this is just to release it. So think back to the formula. Kinetic energy is hc over the wavelength minus the work function. So to just release an electron, that means there's no kinetic energy left over. So use that formula, set kinetic energy is equal to 0, and solve for the wavelength. That will give you the biggest possible wavelength. And then part B, a 3.1 eV photon strikes the surface of sodium. Okay, so that's bigger than the work function. So there's some left over. What's the maximum possible speed? Okay, so if a 3.1 EV comes in, you're using 2.8 EV for just freeing it from the surface. You've got 0.3 EV left over. So that's how much energy you have. Let me actually write this part of it down. Okay, so you've got 0.3 EV left over. You know, how many joules is that? 1 EV, 1.6 to the minus 19th joules. So you can figure out how many joules you have to work with. This is the kinetic energy that we have, remember. That's how much kinetic energy we have. This will give you the amount of joules. That's how much energy you have. It's kinetic energy. That's perfectly good. Don't forget what kinetic energy is, though. 1/2 mv squared. So once you get the amount of kinetic energy in joules, it's an electron, so you know the mass. 9.11, I think it's to the minus 31st kilograms. So once you know the kinetic energy, it's an electron, so you know the mass. Do some algebra, figure out what the speed would have to be. Okay, very good. Okay, so when an ultraviolet photon is absorbed by a molecule of DNA, so you have some DNA, photon comes in, the photon's energy can be converted into vibration energy of molecular bonds. Excessive vibration damages the molecule by causing the bonds to break. So we have ultraviolet light of less than 200 nanometers, okay, causes significant damage to DNA. Ultraviolet light of longer wavelength causes minimal damage, right? Because the lower the wavelength, the higher the energy. So we want to know, what is the threshold energy in electron volts for DNA damage? Okay, so here's the wavelength, 290 nanometers. We want to know how much energy that corresponds to. So this is sort of a biology question. If this is the wavelength, or anything less than that causes damage, how much energy is associated with that? Okay, so you know that the energy is hc divided by the wavelength. Now if you use hc as 1240 eV nanometers divided by 2.9 nanometers, sorry, 290 nanometers, you can figure out the amount of energy that you have then. Okay, so it's really similar to some of the problems we did at the end of chapter 25 in this homework set. So 1240 eV nanometers divided by 290 nanometers will give you the energy in electron volts. Okay, let's look at the next one here. Let's see, a firefly glows by direct conversion of chemical energy to light. The light emitted by a firefly has a peak intensity at 550 nanometers. What is the minimal chemical energy required to generate each photon? Okay, so really, same kind of idea that we had before. If you have 550 nanometers, what energy does that correspond to? So really similar to the previous problem, figure out that energy associated with 550 nanometers. Part B is, given that amount of energy that we just figured out, 1 molecule of ATP provides 0.3 energy when it's metabolized. So if you know the total electron volts from part A, and 1 molecule will provide 0.3 of it, how many total molecules do you have to have? So let me totally read this. 1 molecule of ATP provides 0.3 eV of energy when it's metabolized. What is the minimum number of ATP molecules that must be consumed in the reaction that lead to the emission of 1 550 nanometer photon of light? So figure out the total energy in the 1 550 nanometers, and then you know 1 ATP will provide 0.3 of that. How many ATP molecules do you need in total to add up to the total energy from part A? Okay, very good. Here's another problem we can take a look at. Exposure to a sufficient quantity of ultraviolet will redden the skin, producing a sunburn. The amount of exposure necessary to produce this reddening depends on the wavelength. Remember, lower the wavelength, the higher the energy. For a 1 centimeter square patch of skin, 3.7 millijoules of ultraviolet light of wavelength of 254 nanometers will produce reddening. When you get up to 300 nanometers, which is a higher wavelength, it takes 13 millijoules are required. And the author has worked a similar problem out here. And then we want to know, what is the photon energy corresponding to the wavelength of 254 nanometers? And what is the photon energy corresponding to 300 nanometers? Okay, so you know how to do that already. I mean, if you know the wavelength, you can figure out the energy. Just be careful. The energy they want, the answer here is in joules. So make sure that you convert it to joules. If you use 1240 eV nanometers divided by 254, the answer will come out in electron volts. You'll have to convert it to joules. Same thing with part B. And then part C, how many total photons of 254 nanometers produce this reddening in the 1 centimeter square part? And same question over here, just for the 300 nanometers. Okay, so let's look at part C and part D. Okay, so for part C, for example, let's look at the 254 nanometer wavelength photon. They tell you it takes 3.7 times 10 to the minus third joules of total. This is the total amount of energy. And the 1 centimeter square just describes the little area that's being hit by sunlight. We don't really need this to do any calculations. It just describes what's going on. So this is for part C. Part D is really the same idea. Oops. So for part A, you got the energy that one photon had. This is the total amount of energy to cause reddening. So if you take 3.7 to the minus third joules and you multiply it by, or sorry, divide it by, one photon has a certain amount of joules. This is what you found from part A. This would be the joules, the amount of energy for one photon. This is the total energy, right? That's the total to cause reddening. So if you take the total, it's made up by individual quanta of energy from each photon. This is the total energy divided by the energy for one photon, and you'll see you'll get the amount of photons. It would be something really big, like times 10 to the 15th or something like that. Okay, and then part D is the same idea. We're just looking at the other wavelength for part D. So part A and C go together, part B and D go together. Okay, well, on to the next one. Okay, so let's see. What is the de Broglie, pronounced de Broglie, wavelength of a 171 gram baseball with a speed of 35 meters per second? So everything has a wavelength. I mean, maybe with light it's more intuitive that light would have a wavelength, but baseballs, humans, everything moving has a wavelength. Now your wave behavior doesn't come about until you interact with something on the same scale as your wavelength. So for example, an electron could go through a small opening. Its wavelength is on the same order as the opening it's going through, and wave behavior would come out. For a human or a baseball, there's no way that we're ever going to interact with something with the small wavelength, so our wave nature doesn't come out. We do have a wavelength, though. If you're walking across the room, you have a wavelength. So part A is calculate the wavelength associated with this baseball. Part B is if a baseball had this wavelength, what would its speed be? Okay, so let's take a look at this and see how wavelength and speed and momentum all work together. Okay, so we know from physics 220 that momentum is mass times velocity. Momentum is also equal to h divided by the wavelength. So we could figure out the momentum of a baseball. The mass and the velocity are given. And then knowing the momentum, we can figure out the wavelength. H here is just a constant. So the wavelength would be h divided by m times v. So let's actually figure out what this wavelength is, and then we'll see if a baseball ever can go through an opening on that size. So 6.63 to the minus 34th joules times seconds. Mass, put it into kilograms here, and then multiply it by 35 meters per second. That's a multiply sign. We can figure out the wavelength. So let's actually do that. You can see it's going to be really small, right? So 6.63 to the minus 34th divided by the quantity, 0.171 times 35. Hopefully I got the numbers right. I think it's okay. You might have different numbers than me. 1.11 times 10 to the minus 34th meters. So really, really small. A baseball is never going to go through an opening that small. That's why you don't see the wave nature of macroscopic objects ever, because they're not going to be interacting with anything that's going to be that small. As far as the units go, a joule is a Newton meter, and then we have times seconds divided by kilogram meters per second, and then a Newton is a kilogram meter per second squared. I still have another meter on the top, a second. It's looking kind of ugly, but I think it'll clean up nicely in a minute here. Okay, kilogram meter per second. So one of these seconds here cancels. There's a kilogram and a kilogram. Those cancel. There's a meter and a meter. Those cancel. Let's see. Here's a second and here's a second. So this second would come up to the numerator. This second is in the denominator. The seconds cancel. And the only thing we're left with is meters then, which it should be. Everything's in SI units, but as you see it does come out in meters. So really small wavelength associated with the space ball. Part B is if the wavelength was 0.3 nanometers, what would the speed have to be? Okay, so you use this relationship kind of knowing something else, figuring out what the speed would be. So maybe if you want to go back to this one actually, and we want to figure out the speed. So the speed is h divided by m times the wavelength. Whoops, you can't see that. There we go. So using this equation up here, just solve for the speed. That's what I have here. So Planck's constant, it's just a constant. The mass was already given. Now they're giving you this new wavelength. What would the speed have to be to have that kind of wavelength? Let's actually see it. This should be pretty interesting. 6.63 to the minus 34th. Everything's going to be in SI units, so I'm not going to write the units. I'm running out of space here. 0.171 times the wavelength, 0.3 nanometers, so to the minus 9th. Okay, so put all that together and figure out the speed then. Okay, very good. Okay, so in this problem, investigators have created structures consisting of linear chains of ionized atoms on smooth surfaces. Electrons are restricted to travel along the chain. The energy levels of the electrons match the results of a particle in a box model. So take a look at that section from the book, a particle in a box. The idea behind it is if these particles have a wave structure, and these are standing waves, the standing waves can only have be confined to certain areas and have certain frequencies. Just like in Physics 220, when we built standing waves, we had a string that was vibrating, and we could produce several different antinodes and nodes, but there are only certain complete wavelengths. It's the same thing here. We can only have certain allowed wavelengths. So review that section in the book. But that's the idea. It's really just like standing waves on a string. These waves have to fit in certain confined areas, and they have exact energies for those states. So let's see how this actually plays out. So just to refresh your memory, this is what I was talking about with waves on a string. You can only have certain antinodes, like this one would have 3 antinodes and 4 nodes. We did this experiment in Physics 220. So if you have the wave nature of particles being expressed, you can only have certain wavelengths. So, you know, there can only be a certain wavelength here if you have an actual something that looks like a standing wave. So the condition that we had before, this goes back to Physics 220, chapter 16, the wavelength was 2L divided by N. So there are only certain wavelengths that are allowed. So if you have a particle trapped in a box, it can only have certain wavelengths. This describes the wavelengths. And now we know from the de Broglie relationship, if you have certain wavelengths, then you must have, each wavelength goes along with a certain amount of energy. So there's only certain wavelengths that are allowed. 2L over N, so 2L divided by 1, that would be like sort of the fundamental frequency idea we did before. 2L over 2, 2L over 3, those are the only allowed wavelengths. And then associated with those wavelengths are momentum, which we just saw in the de Broglie relationship, and also a certain amount of energies. So if you put that all together, this is the relationship for momentum. Energy turns out to be momentum squared divided by 2m. Put that all together, you get this formula here. So if you have a particle in a box, which is what we have, that's what they told us, it could be modeled as a particle in a box, this is the energy. So when n is equal to 1, that's the ground state energy. In this formula, h is Planck's constant, 8 is just the number 8, m is the mass of an electron, so you'll have to, I gave that out earlier. L is the length of the box, n indicates which energy level we are at. So you could figure out E is equal to 1 by putting 1 in for n. Now this is going to come out in joules. You'll have to turn it into electron volts. Okay, so do that for n is equal to 1, n is equal to 2, n is equal to 3, and get those first three energy levels. Now if you want a little shorthand cut way of doing it is just get the first one when n is equal to 1, again convert it to electron volts, and then the upper level energy levels are just multiples of that. So when n is equal to 2, take the ground state, multiply it by 2 squared, or in other words multiply it by 4. To get E sub 3, multiply the ground state by 3 squared, or 9. Okay, so the difference between the quantum mechanical world, which we're talking about these days, and the everyday world. In the quantum mechanical world, you can only have certain allowed energies. These are just discrete amounts of energy. So an analogy would be, if I'm going into the tech building, I climb up the steps. I can go that direction into the tech building. So I've got maybe no energy on the ground level if I'm thinking of gravitational potential energy, and then I could be on the next step or the next step. I can't be anywhere in between those. That would be the quantum mechanical world. In the regular world that we're used to, I could just take the ramp up and then I could be anywhere I want to. But in the quantum mechanical world, you can only have a certain amount of energy, just discrete amounts of energy. Okay, so you have everything to solve this problem then. All right, let's look at the next one. Good, so this is a picture, this is an energy level diagram, and we want to know what wavelengths appear in the energy spectrum. So the way this works is, if you're on the ground state, you can grab a photon and go up to the n is equal to 2 level. So if you're absorbing photons, you can go from 1 to 2, or you can go all the way from 1 to 3. Now the emission spectrum works in reverse. So if you're an electron up here, you could drop from 3 all the way down to 1. You could drop from 3 only down to 2, or you could drop from 2 down to 1. Those are those discrete steps. So there's going to be 3 wavelengths in the emission spectrum. The 3 again, just to refresh your memory, because I just said it though. It's not much of a refresh, I suppose. Just to recap though, I can go from 3 to 1, I can go from 3 to 2, or I can go from 2 to 1. So there's going to be 3 wavelengths in the emission spectrum. So let's actually write this out. We'll use a lot of the ideas that we've already used talking about the energy of a photon. But let's look at this. So here's the transitions allowed from 3 down to 1, or from 3 to 2, or from 2 to 1. So when you go from 3 down to 1, this difference is 4 eV, right? 4 minus 0. When you go from 3 to 2, that difference, 4 minus 1.5 would only be 2.5. That's the difference in energy level. So from 4 to 1.5, that would be 2.5. And then when you go from 2 to 1, this energy difference is 1.5. So when you drop down in energy, you emit a photon. So let's just do one of them. It's the same thing here. So energy going from 3 to 1. The difference in energy would be 4 eV, and we know energy is hc divided by the wavelength. So the wavelength then would be hc over 4 eV. Right, just do a little bit of algebra. That goes here, this comes there. Now if you use 1240 eV nanometers divided by 4 eV, this will tell you the wavelength of the emitted photon. Luckily the math is not too bad here. This would be 310 nanometers. Oops, running out of space. Okay, let me just recap again. So solve for the wavelength, hc over 4 eV. Now when you use our nice little hc is 1240 eV nanometers, then this makes it a lot easier. So 1240 eV nanometers divided by 4 eV, the answer comes out in nanometers. Now when you go from say 3 only down to 2, that energy difference is 2.5 eV. So the energy, again, hc divided by the wavelength. So then the wavelength is hc over 2.5 eV, just like we did on the previous problem. And again, if you use 1240 eV nanometers, this comes out to nice and clean. The EVs cancel out, and you're just left with whatever nanometers this is. Okay, same idea from going from 2 down to 1. And then list all 3 answers with commas separating them. Good, so hopefully you see the nice way of looking at HC. If the answer is in nanometers, it simplifies things a lot. All right, on to the next one. Well, this one doesn't have a nice little chart, but it's the same problem, really. The allowed energies of a quantum system are 0, 6, and 8. So just think of that last picture. Instead of it being 0, 1.5, and 4, this is 0, 6, and 8. What wavelengths appear in the emission spectrum? So same problem. There should be 3 of them, right? Going from the third one to the second one, from the third one down to the first one, or from the second one to the first one. So it's really the same problem, just not with a really nice picture. So, take a look at that one. And the final one. What is the linear size of the smallest box in which you can confine an electron if you want to know the uncertainty in the speed to no more than 18 meters per second? So this is something called the Heisenberg uncertainty principle. Now, in our world, we could pretty much narrow down where something is, where it's confined to, and how fast it's going. Strange things happen when you get to the quantum mechanical level. The more and more you know something about the speed, the less and less you know where it's at. The more you know where something's at, the less you know about its speed. That's the way the quantum mechanical world works. So again, review the appropriate section in the book, and let's take a look at this. Okay, so this is Heisenberg's uncertainty principle. This means uncertainty in position times the uncertainty in the momentum is greater than or equal to h, Planck's constant, divided by 4 pi. Now they give us the speed, the uncertainty in the speed in this question, but it's an electron, so I know the uncertainty in the momentum is just m times the uncertainty in the speed. So let me kind of rephrase this question. M times the uncertainty in the speed greater than or equal to h over 4 pi. And they're saying, what is the uncertainty in x? That's really what they're asking in this question. So we know everything except for what we're looking for. The uncertainty in the electron's position greater than or equal to h, and then divide both sides by m, uncertainty in speed. So this would be m, uncertainty in speed. Don't forget we still have a 4 and a pi down there. So then this will give you the uncertainty, the minimum uncertainty in where it's actually confined, the uncertainty in x here. Okay, so if you look at it, the smaller and smaller you make this, mathematically speaking, the larger you're going to make this. Okay, so put the numbers in there, you'll get the uncertainty in the position. Okay, so that's the last problem on this homework set, actually. So we've made the leap, the quantum leap, if you will, into quantum physics, and we're looking at looking at light as behaving like a particle in some sense. So in this chapter 28, we had the photoelectric effect. We just did one of these Heisenberg uncertainty principle ones. But I would say the biggest thrust of chapter 28 is looking at the energy that a photon has and under different conditions, and looking at the photoelectric effect. Also, we did a few particles in box problems. Okay, so one thing about this, I mean, it's very abstract maybe, which actually that makes it pretty cool, but they're very specific. So when it's a photoelectric problem from the problem, I always say like F is equal to ma. You could use that for almost anything. That's what makes it really challenging. Like, what formula do you use, that sort of thing. But with the photoelectric effect, you've only got the photoelectric effect formula. So it narrows it down in terms of a problem-solving process. Photoelectric problem, here are the photoelectric equations. Just you have to keep in mind the concept from which the equations came from. Okay, anyway, if you have any questions, email me. We can set up any kind of WebEx meeting you want to, and hope to see you soon, actually, via the internet. Talk to you later. Bye-bye.